Right, cool, cool, cool. So we are officially in Unit 3. So our third, I guess technically our fourth unit if you count 2B as its separate unit, but we are in our next unit, I guess, Unit 3. So Unit 3, yay, first day. All right, and this unit is technically called like the application of derivatives, but we've already looked at a lot of application with derivatives so far. In this unit, we focus more so on the characteristics of the graphs of the derivatives, the first and second, and the original function. We focused a lot on that. And there is another type of application similar to related rates that we're going to talk about in this unit as well. But for the most part, the first good chunk of this unit is describing characteristics of graphs. And I think a good first day to start off with is describing maxes and mins of graphs and how they relate to derivatives. I think that's a great place to start because we already have a general idea of what these what maxes and mins are. So let's kind of look into it. It says given a function f that has some value c in the domain of D, we say f has, and then it jumps down to these four definitions. So we'll talk about those four definitions in a second. Let's first label each of these on our graph. And the reason I'm doing this is because we already know what these are, and I just kind of want to make sure it's clear. So for instance, this is a closed interval. I just drew a random function, and you can sketch it right now. I labeled a bunch of different points on here to describe stuff. So we're going all the way here from A all the way here to G. Okay. All right. Now, this point here, this point here, what do we call those? Those are relative, or another word that we hardly use but sometimes comes up is local. So relative or local maxes. Okay. Same thing here. I'll draw an arrow. So both of these are relative local maximums. Okay, I mostly just say relative. So this is relative max. And right here, I think it's clear to say that these are relative or local mins. Okay. Now I think we can tell why. I mean, obviously at these points, it's like being on the top of a hill or at the bottom of a valley. Either way, you can tell that locally, all right, keyword locally, it is a max or a min. It's not the overall max, it's not the overall min, because there are values higher than them on or lower than them on this curve, but relative to around their general area, they are considered maxes and mins. What about this point right here? If I were to draw a horizontal tangent line to it, okay, is there any point on this graph, on this closed interval, that is greater than that point? I think you can tell that the answer would be no. So what we call those is an absolute extrema. In this case, it's an absolute maximum. Okay. Now, something that I wanted to point out, and I know this is going to seem weird, but we know what relative means. We know it's relative. We know that relative can never be absolute because we're not, a relative minimum or maximum is relative to its area. But an absolute max can also be labeled as a relative max because technically it is relatively a maximum, but it also happens to be an absolute maximum. Okay, so they're all called relative max and mins, but sometimes they can be labeled absolutes. Okay, so just kind of keep that in mind. The biggest and smallest values can be called absolute, can be called relative. Let's talk about the endpoints. Let's talk about A and G and how endpoints work on a closed interval with max and mins. So let's kind of write this separately here. Endpoints. So the domain all right, okay, let's put it this way. Intervals, or the endpoints, can be considered an absolute max or an absolute min. So let's write it that way. Can be, keyword emphasis on can be an absolute max or min. Never relative. The reason is because whenever we're looking at a closed interval, it means we're kind of cutting the graph off at these points. Now, I don't know what's going off to the left of A or to the right of G, but without that information, we can't talk about it relatively. All right, we can't talk about it as a relative max or min. I don't make the rules, somebody else did. But on a closed interval, we can discuss them as absolute maxes or absolute mins. So for instance, right here at G, it is not the highest point at all on this graph. So it is not an absolute max. It's not even a relative max or a relative min because endpoints can't be that. But at A, since it is the smallest value on this closed interval, can be considered an absolute minimum. So endpoints, again, can be an absolute or max, but never be a relative. Or they could be neither. Endpoint G is neither. So again, we've seen these before, just kind of refreshing you a little bit. And here's the four definitions kind of spelled out for you. Absolute max, absolute min. At A, if f of A is greater than f of x for all of x, f of A is called the maximum. And if f of A is less than f of x, meaning it's the smallest y value for all of x, it's called the absolute minimum. And these can potentially be endpoints. Now, local or relative max and mins means that if we have f of c is greater than f of x when it's near c, then it's a relative max. And if f of c is less than f of x, so we have a minimum when it's only near c, then it's considered a relative minimum. So ideally, we know what these mean. Okay? All right. I have a few examples that we can look at maxes and mins and absolute maxes and mins. I mean, x squared plus 1, x cubed, sine of x. You've seen all these before. I'm just going to skip down to the fourth example. And I don't think we need much more than that. So, all right. I encourage you to graph this function. I encourage you to graph this function on your graphing calculator or in Desmos. I'll just show you real quick what it looks like. I'm not testing us on finding these values yet, but oh, it's not going to raise them to the power. So this is what my graph looks like. So we have some stuff going on here. Okay, looks like we have a point here at 0, 0, a point here at 1, 5, and a point down here at 3, negative 27. So I'm going to take a second. I'm going to kind of graph this and sketch this on whiteboard so we can discuss it for a second. But maybe you graph that as well. Okay, so we got our little sketch right here. And let's label all the different categories. Let's talk about like local, and there I go. I always say relative. I shouldn't stick with local. I hate that. I like saying relative. Relative max, relative min, absolute max, and absolute min. All right. Relative max are relatively maximums, and I think we can tell that 1, 5 is that point. So we have a local maximum at x equals 1, and it equals 5. So like that can be asked a number of different ways. I can ask for the point at which we have a relative max, or I can ask for the actual value. The point would be 1, 5, and the actual value would be 5. I mean, that's the value of the relative max. The relative mins, it looks like we have 2 of them. All right, we have one at 0, 0, and 3, negative 27. It just turns out that nothing is ever going to go below 3, negative 27, so that relative minimum is also an absolute minimum. Nothing goes below that. So the absolute minimum value in this case is that negative 27. It occurs at 3. Now, what about the max, the absolute max? We got a relative one here, but if you notice, there is no endpoints, and that this function goes on to infinity. So it's unbounded, meaning that there is none. Okay. So there you go. Now, what if there were endpoints? What if I gave a constraint? What if I said on the interval, what if I added this stipulation? On the interval, and I said, how about we include -1 to 4? So looking back at Desmos, let's just see what those values are. Oops. At -1, well, that's really high up there, isn't it? -1, it is, I think, 37. Yeah. So -1, it's 37. And looking at my sheet here, negative or +4 is +4, I think is 31. 32. So it's 432 and -137. So let's go back. So let's say that we decided to restrain this graph. And like right here and right here, it looks like we said it goes -1 all the way up to 37. And it looks like that it goes from up to 432. Okay, cool. Now, what if I did that? What if I decided to make it an interval? Does that change anything? Well, it doesn't change the relative stuff. So that's still a relative max, and that's still a relative min. Okay. And in this case, it doesn't change the fact that we have an absolute minimum. That did not change the absolute minimum at all. The only thing that this now changes is what endpoints can be is an absolute. The absolute min's unchanged, but now we do have an absolute maximum. The absolute maximum value is at the endpoint -137. The value is now 37. Nothing goes above that. So constraining a graph with endpoints can either have us to have an absolute max or an absolute min, which leads us kind of to our next thought here with our theorems. The extreme value theorem. So the biggest and really only main theorem we've learned so far is the intermediate value theorem. The extreme value theorem is important. It's very helpful. We don't use it as often, but it does come up sometimes. It states, if f is continuous, so continuous on the closed interval a to b, then f is going to obtain an absolute maximum value, f of c, and an absolute minimum value, f of d, for some number c and d and a and b. All right, I know that's a mouthful, and I'm about to graph it here in a second, but I kind of went ahead and did this already. If you notice, before in example 4, we had no absolute max. We did have an absolute min. When I put a constraint on it, it looked like this, I forced us to have an absolute maximum. Absolute max, and we already had an absolute min. That's what the extreme value theorem says. It states pretty much that if we have a closed interval, we are guaranteed to have an absolute max and absolute min. I mean, since it's closed off, one value is going to be bigger than all the rest, and one value is going to be smaller than all the rest. That's what the extreme value theorem says. Now, this is just an existence theorem. It doesn't tell us how to find any extreme values. It just says they exist, just like the intermediate value theorem. Okay. So how do we figure out where we have any local max or local mins? Let's say we have a graph that looks like this. How do I identify any local maxes? And how do I identify any local mins? Calculus-wise. All right, the extreme value theorem can state that we have some absolute max and mins. It doesn't talk about how to find any local max or mins. Well, I'm sure you're probably already figuring this out. At extrema, we have horizontal tangent lines. Another way of saying that is when f prime of x equals 0. And we've already touched on this so much, but now we're kind of putting it into an official lesson here, that anytime we have f prime of x equals 0, we should be at a max or a min. Okay. So let's kind of go with that. This is where our math starts to come into place. Now here's Fermat's theorem. Never, ever, ever, ever do we use this theorem. It's just kind of, we never say by Fermat's theorem. We do say by extreme value theorem, but we never say by Fermat's theorem. All it's stating is what we already know. If f has a local max or minimum at C, so if we have a max or minimum, max or a minimum at C, and this is very important, if f prime of C exists, then f prime of C equals 0. So if f prime of C equals 0, then we have a local max or local min. Now, this is not, let me explain, this is not an absolute theorem. Not an absolute theorem. There are exceptions. Examples that could occur is that we could have a vertical tangent or sharp point. Another way of saying that is where f prime of C does not exist. Let me give you an example. The absolute value graph. Okay. So like right here at this point, this is a minimum. But f prime of C does not equal 0. F prime of C does not exist. Okay? So there's a perfect example of what I'm trying to explain. This is a minimum value. This is a minimum value. But f prime of C does not equal 0. So we can't always go based off of the fact that f prime of C means we have a max or min. We sometimes have to consider when f prime of C does not exist, because that could be at sharp terms and stuff like that. So what can we gather from this theorem? We should at least start by looking for extreme values where f prime of C equals 0 or where f prime of C does not exist. Those tell me where I have maxes or mins, because that's where I have vertical or horizontal tangent lines. We know this already. So which leads me to the math for today, which is what I've been trying to get to. Critical numbers is a term I'm going to use so much now. A critical number is just where the derivative equals 0 or where the derivative does not exist. It's at these points that we could have, and a lot of times it does work out this way, but this is where we have potential, I guess is the best word to use, potential max and mins. More ideally, local max and mins. Could be absolute, but mostly local max and mins. And it's real easy. We've done this before. We just find the derivative, set the derivative equal to 0, and solve. But number 3, we haven't really done much. Check for any places where the derivative doesn't exist either, because it's not always where the derivative equals 0. It's sometimes where the derivative does not exist. Then we can have our max or min. Think of absolute value again. That's a good example. Okay. Now, to find absolute max and mins, this is a little bit different. Absolute max and mins is we're going to find all the critical values. Okay, that's a good place to start. And we're going to find the y values of those critical values. So we're going to see like which one's the bigger ones or the smallest ones. But we also have to consider endpoints. This is very important. For absolute max and mins, if we're on a closed interval, we also have to include endpoints. And whichever one's the largest is the max, whichever one's the smallest is the absolute min. And that's how that works. Okay. So I got a couple of examples. Now I might try to get through all of them for for us, and so I can just go through and review. But right here, okay, number 4, let's start by finding the critical numbers. Let's find the critical numbers. And all that means is find where f prime of x equals 0 or does not exist. Most of the time, it's just going to be where it equals 0. Okay? All right, so f prime of x equals 3x squared minus 2x minus 1. And I'm trying to figure out all the places where this equals 0 or does not exist. Well, there are no places where this does not exist. I can plug in any value for x and it works out because it's a polynomial, but I can solve where this equals 0. This factors to 3x plus 1 and x minus 1. So this equals 0 when x equals negative 1/3 and x equals 1. So what we just found right here are the critical numbers. And we've done this so many times before. We've just called them, we just said they were horizontal tangent lines. But ideally, these are potential relative max or mins. We'll have to figure out which is which later on down the road. But right now, we're just practicing finding critical numbers. Okay. So example 5 says, find the critical numbers of this equation. All right, well, this one's going to be fun. Let's try this one out real fast. So it looks like it's going to be product rule. So f prime of x equals, it's the derivative of the first, which the more I look at this, I think it's going to be a lot easier for us if we distribute the value first. Let's say 4x to the 3/5. We can say this is x to the 5/5. If I multiply those, we're really adding them together. So that's going to be x to the 8/5. I think that's going to make our life a lot easier to take the derivative. But if I take this derivative, bring the power down, so 4 times 3/5 is going to be 12/5 x, and if I subtract a power from that, it's going to be negative 2/5. Okay. And the other one's going to be minus. I bring the 8/5 down, and it's x to, if I subtract a power from that, it's going to be 3/5 power. Okay. Now to solve for the critical points, we're just trying to solve for all these equals 0 or does not exist. So what values of x make it 0 or does not exist? By definition, that's what a critical number is. Okay. All right, so first things first, if I'm solving this, let's maybe simplify it a little bit. Let's do 12 over 5, x to the 2/5, so bring that power to the bottom. And we still have 8, x to the 3/5 over 5. If I want to combine these together when I'm solving for 0, maybe we should get a common denominator. And it looks like the common denominator is just going to be x to the 2/5 on top and bottom here, and then we should be good to go. So I got 5x to the 2/5 on bottom, and on top I got 12 minus. If I combine these two together, add them together, it's 8x to the 5/5, or just 8x. So that works out pretty nice for us. And we're going to set this equal to 0 or does not exist. Now, unlike the last example, there is going to be values that do not exist. So there will be other critical points. They come from setting the top equal to 0 to find the ones that equal 0. And if we set the bottom equal to 0, that's where we're going to find that it does not exist. So for the critical numbers here, the ones that makes it equal to 0 is going to be, so I'll do this, 12 minus 18x equals 0. And I'm going to do 5x to the 2/5 equals 0. The ones that make it equal to 0 is going to be 12 equals 18x, or x equals 12 over 18, which is what? 3/6, or divided by 3 is going to be 4/6. Man, am I really butchering this? Divided by 2 is going to be Wait a minute. I'm confusing myself now. I can't simplify. I'm pressured to simplify here. Divide by 6 is going to be 2/3. My goodness, that was rough. So what makes it 0 is 2/3, and what makes it does not exist is just going to be 0. So we have two critical points here. One makes it 0, one makes it undefined. Now, either one of these, again, are potential maxes and mins. We'll just have to prove that later. Okay. Now, we practice finding the critical numbers. I actually want to do an example where we find the absolute maxes and the mins, or relative maxes and relative mins. So we'll end with this example here. It says find the absolute max and min on the interval -1 to 2. So we have a closed interval here, and it's of this function here. So without a graphing calculator, we can figure this out. Remember the steps. Step 1 is to find all your critical points. And if we have endpoints, label your endpoints. And then we just find the y values of all of those and see which one's the biggest. Okay. So number 1, critical points. We do that by taking the derivative. So I'm going to do chain rule here, which we should be pretty good at chain rule by now. Multiply by the derivative of the inside. And I'm going to set this equal to 0 and solve. And also values where it doesn't exist. But again, this is a polynomial, so we shouldn't have any of those situations. Okay. All right. Well, I could solve this out, but because it's already in factored form, I can set each one of these equal to 0 and solve. So I can say like x squared minus 1 squared equals 0 and 2x equals 0. There's no sense in trying to distribute everything because it's already in factored form. So that can never happen. That's not one. But right here, we could take the square root of both sides, get x squared minus 1 equals 0. We can add 1 to both sides and then take the square root and get plus or minus 1. And over here, x equals 0. So my critical points that I got by setting the derivative equal to 0 are 0, 1, and -1. All right. So step 2 is going to be find the y values of the critical points. And I'm going to go ahead and combine that with step 3, which is to find the y values of endpoints. We're going to find the y values of all of these. And then all we have to do is compare. Okay. So my interval is between -1 and 2. So I'm going to put f of -1, which happens to also be a critical point. So I don't have to label that twice. We also have the point f of 0 as another critical point. We also have f of 1 as a critical point. And my last endpoint is f of 2. So I'm considering the endpoints, I'm considering the critical points. And how we get this is we just plug these back into the original equation, right? So this is going to be, instead of x squared minus 1, this is going to be -1 squared minus 1 to the 3rd power. And this is going to be 0 squared minus 1 to the 3rd, 1 squared minus 1 to the 3rd, and 2 squared minus 1 to the 3rd. All right, this equals 0. This equals -1. This equals 0. And this equals 27. So comparing the two together, we would say that this is my absolute maximum value, and this is my absolute minimum value. So without graphing it, without having to do any work with the calculator or anything, I was able to identify my absolute max and my absolute min on this interval. Okay. So we're going to practice a lot more of this stuff in class, as well as do some more examples of this in the next lesson. So, whoa, right here at 30 minutes, that worked out pretty good. And we finished the entire lesson, so in class we can just review everything. All right, well, there's your little intro today. Hopefully it made some sense, and y'all have a fantastic day.